Greetings, SERDP webpage browsers. I'm Mandy Michelson here with Carla Ng and Jennifer Field, and today we're going to introduce ourselves, and then we'll give you the scoop on SERDP project ER 181417. So again, I'm Mandy Michelson. I'm a civil environmental research engineer with the U.S. Army Engineer Research Development Center, ERDC for short. I spent the past 15 years thinking about cleaning up groundwater contaminated with chlorinated solvents and explosives, and have to say that PFAS, which stands for perfluoral and polyfluorinated alkyl substances, kind of make explosives and chlorinated solvents seem boring.
Hi, I'm Carla Ng. I'm an assistant professor of civil and environmental engineering at the University of Pittsburgh. And I've been working on PFAS modeling for about the last 7 years, focused on their accumulation and distribution in organisms. And the models I develop in my group are based on the idea that PFAS protein interactions can influence their tissue distribution, biological persistence, and the potential toxic impacts of PFAS.
Hi, I'm Jennifer Field. I'm at Oregon State University, and I'm an environmental analytical chemist, and I have worked on PFASs for more than 20 years now. My research focuses primarily on the development of analytical methods for PFASs in a variety of matrices, and then the application of those methodologies to understand the fate and transport of PFASs in the environment. Areas of interest include the fate and transport of PFASs in water, soil, and sediment, in these natural systems like groundwater, lakes, and rivers, but also in engineered systems, including wastewater treatment systems and landfills. As you may know, PFASs are making news around the country because they're increasingly detected in drinking water supplies. And we now are beginning to better understand the sources of PFASs and how and why they're impacting our water sources. For example, we know that residues from firefighting foams used at military and civilian locations have impacted water supplies. We are also increasingly aware that there are fluorochemical manufacturing sites that have emissions to air and water, as well as the application of oil and water repelling treatments to consumer goods, and those uses and then the use and disposal or washing of those consumer goods has led to landfills, effluents being contaminated with PFASs, as well as wastewater treatment plant emissions in the form of biosolids, which can go on to land, as well as effluents that can impact surface waters. Many of the PFASs of interest, including this project, are water-soluble, and they then move readily through the environment, including penetration of soil environments to reach groundwater or runoff into surface water supplies. So that's how they end up in our drinking water and irrigation waters. Two of the most well-known PFASs that we're also studying is PFOS and PFOA. And these are just single members of families, and these families are of interest with regard to human environmental exposure. Both PFOS and PFOA and their carbon chain link family members have no known biodegradation pathways, so they're very persistent in the environment.
Unlike traditional persistent organic pollutants, PFAS are charged at environmentally and biologically relevant pH and don't accumulate in lipid tissues. They are also much harder to remove from water using traditional methods due to their relatively high water solubility and mobility. The central hypothesis behind this interdisciplinary and collaborative project was to harness the observed tendency of PFAS to interact with proteins and harness that ability to design effective and environmentally relevant protein-based sorbents for PFAS removal from drinking water.
And previous PFAS research had already given us some clues as to which proteins could have strong interactions with certain perfluorinated alkyl acids and thus be good candidates for these environmentally friendly sorbents. But we wanted to screen a wider variety of proteins and other biomolecules as potential sorbents for both long-chain and short-chain perfluoroalkyl acids. So to do this, we used molecular dynamics, which is a framework we recently developed in my research group at Pitt, using computer simulations to estimate the relative strength of interaction between proteins and certain PFASs. So we looked for protein candidates that were simple, with one primary binding site, and had a relatively small size so that it would be easy to eventually produce these at larger scale. Once the screening process identified likely candidates for both long and short-chain PFAS, these were liver and intestinal fatty acid binding proteins and 3 peroxisome proliferator activated receptors, or PPARs, termed PPAR alpha, beta, and gamma. We then experimentally verified our modeling predictions using equilibrium dialysis.
To clarify how this technique works, Because the protein molecules are a good bit larger than the PFAS molecules, the proteins can be suspended behind a molecular weight cutoff membrane so that the PFAS molecules can exchange freely in solution with the protein. And then after 48 hours on a shaker table, the concentration of PFAS remaining in the dialysate was quantified so that we could determine how much PFAS sorbed to the protein by difference. In other words, the initial PFAS concentration in the buffer solution minus PFAS in solution after the equilibrium dialysis testing was equal to the mass of the protein, the mass of the PFAS bound to the protein. This, of course, required confirmation that PFAS sorptive losses weren't occurring in the experimental system.
And that's where analytical chemistry comes in. Analytical chemistry is being used to support these laboratory protein binding measurements. And in order to do that, we really have to be able to analyze quite well the PFASs that are in solution before and after the proteins are introduced. Quality control is very important because we have to ensure that the losses we are attributing to proteins is not due to losses onto, say, experimental systems like tubing, for example. And so great care is taken to make sure that the concentrations that are determined are quite accurate, and we're always in a process of eliminating any potential sources of bias or error. And as part of that, we're capturing the variability in the measurements so that that uncertainty is communicated as we interpret the final data with regard to protein binding with PFAS.
So what did we find? This one-year limited scope project produced some really tantalizing results, including suggestions that proteins could be as or more effective at removing PFAS from an aqueous matrix than traditional approaches. So, for example, we found that PPAR-gamma had an equilibrium binding capacity for PFAS that was at least as strong as any competing traditional technology, including both activated carbon and anion exchange. Even more interestingly, liver fatty acid binding protein bound strongly to PFHXS, the 6-carbon sulfonate, at low pH, and also to PFBS, the 4-carbon sulfonate. PPAR-alpha and PPAR-delta also showed capacity to bind to PFHXA and PFBA, respectively, though not as strongly as the other pairs. So this is the first time that strong interactions were observed for some of these short-chain PFASs that are so difficult to remove from drinking water. Based on these promising results, we're really looking forward to further assessing the kinetics of interactions of PFAS and these selected proteins through planned batch and flow-through experiments in a follow-on project next year.
How cool would it be if we could make a new kind of faucet filter that would get these PFAS contaminants out of our water? Right?
Agreed.
Well, thank you, everybody, for stopping by SERDP 181417 website.